Hi everyone, welcome to this webinar series, which is MI2, Machine Intelligence and Modern Infrastructure. My name is Janaki Ram. I'm a Google developer expert, an Intel software innovator, Microsoft MVP, focused on cloud and AI. So if you're attending this series for the first time, let me set the context. So what exactly is MI2? So MI2, it's an emerging technology concept where we have the convergence of machine intelligence on modern infrastructure. So as we know, infrastructure is primarily shifting from virtual machines and physical hosts to more of containers and cloud native. So modern infrastructure is predominantly driven by Kubernetes and related technologies. So that is the foundational element of the new stack. And on top of that, we are going to see modern workloads driven by intelligence. And the machine intelligence workload is predominantly IoT, deep learning, artificial intelligence, neural networks, and so on. And as we see the convergence of these two layers, we are going to shift into the new paradigm where applications are going to be deployed as microservices and intelligence is going to be infused through deep learning and neural networks. This webinar series tries to bring the convergence of these two emerging technologies. This is completely neutral, independent, unbiased platform to explore and learn emerging technologies. So if you have been following this series, I covered a variety of technologies from Kubernetes to service mesh to serverless computing, and of course, a variety of AI accelerators and edge computing platforms. And this time, I'm very excited to bring you the ability to run TensorFlow models on Edge TPU. So Edge TPU is, again, a very new technology from Google. It is bringing the cloud TPU into a very miniature form factor that runs on devices like Raspberry Pi Zero and even some of the upcoming system on board and system on chip devices. So I'm going to walk you through what exactly is the TPU and why Google created the TPU. And then we'll understand the differences between cloud TPU and the edge TPU. Then I'm going to talk about two mechanisms which will help us deploy machine learning models on the edge TPU. One is using AutoML vision where we don't need to write code. The second one is slightly more advanced but gives us more control, which is using transfer learning to take an existing neural network architecture and training a custom model from that. So like most of my sessions, I have very few slides and more demos. So before I go any further, let me make sure I understand where you are in your machine learning and deep learning journey. So tell me how familiar you are with TensorFlow. This would help me tune the content based on your background. All right, so looks like most of you have only played with the MNIST model for experimentation, and majority of you have never used TensorFlow, which is absolutely fine. And some of you have actually gone ahead and deployed TensorFlow models in production, which is excellent. All right, that does give me a sense of where you are in your journey. Now, let me walk you through some background concepts, set the context for running TensorFlow models for inferencing on Edge TPU. So what exactly is the GPU? And it's very important for us to understand this before we can appreciate the power of TPU and particularly the Edge TPU. So CPU has been the building block of computing for last 4 or 5 decades. And because of that, the CPU is a very generic processor, which is not really meant to do custom computing, as in any line of code that we write, any kind of application that we run, any workload that we deploy is ultimately going to be treated exactly the same by the CPU. So it's general purpose, its architecture is very generic, and also it has become a very standard element in the computing stack. Now, as software evolved, and particularly as we started to use some of the emerging technologies, particularly in the field of high performance computing, gaming, and genome modeling, and so on, CPUs have fallen short of certain capabilities. And those capabilities are related to intense mathematical computations. The CPU is not just designed to deal with massive parallelization. It typically works in a sequential form. It processes instructions in a sequence, and because it is very fast, we don't really realize that. But it becomes very obvious when we run parallelized operations, particularly things like video rendering or gaming, or machine learning and AI inferencing and so on. So to give you a sense of where CPU stands and where GPU comes in, if you actually take an Intel Xeon Platinum 8180, which is a very powerful CPU, it comes with 28 cores and operates at 2.5 gigahertz frequency. It can process about 2240 G-flops. So a G-flop or a gigaflop is essentially a billion floating point operations per second. And it is a lot. Most of the workloads are just fine with that kind of speed and that kind of horsepower. But when we run mathematical computations and particularly matrix multiplications and tensor operations, this is just not sufficient. Now let's take one of the popular NVIDIA V100 Volta GPU. This comes with 80 cores and operates at a frequency of 1.53 gigahertz. And just in terms of its horsepower, it can process about 7,000 gigaflops. Now, what happens when we actually add a GPU to our CPU? It complements CPU while CPU continues to do general purpose computing and processes x86 instructions. Mathematical operations are going to be offloaded and delegated to the GPU. So all the matrix multiplications and tensor calculations and all the heavy lifting essentially moves to the GPU, while the CPU continues to deal with the regular x86 set of instructions. Now, when we combine these two, it forms a lethal combination and gives us a very powerful environment to not only deal with complex software, but also perform high performance computing or basically run high performance workloads. And that's the reason why we notice GPUs are being added to gaming consoles like Xbox and PS4, and even high-end gaming laptops come with GPUs. But that's just one use case. Since machine learning and artificial intelligence deals a lot with mathematical computation, GPUs have also become very critical for training and inferencing machine learning models. So that led us to use a combination of CPU and GPU, and today it's a very common architecture where we launch an Intel Xeon based machine in cloud maybe, and then also choose a GPU configuration, something like a P100, a Pascal 100, or a K80 based GPU from NVIDIA. Now, if that is GPU, what is TPU and what is Google doing here? Well, GPU predates machine learning and artificial intelligence. When NVIDIA created GPUs, or for that matter, even AMD and even Intel, when they created GPU, machine learning was not the topmost workload. It was essentially created for general purpose parallelization and general purpose computing. But it also became the essential building block for machine learning and artificial intelligence. So in a lot of environments, there is a layer that bridges a machine learning framework like TensorFlow with the underlying GPU. And that layer is very proprietary to the GPU provider. For example, when we run NVIDIA, we use something called CUDA, which is a compute unified device architecture. And that is going to be the layer which performs parallelization. And this is further exposed via a library called cuDNN, which is a CUDA-based deep neural network library. And this cuDNN is ultimately exposed to TensorFlow, MXNet, CNTK, PyTorch, and so on. So that stack is highly customized for machine learning, and that's how we exploit the power of GPUs from modern contemporary machine learning frameworks like TensorFlow, PyTorch, and Caffe. So Google realized that GPUs, even though they are very good for machine learning and AI, they're not purpose built only for AI or machine learning. And they bring a level of overhead, and also they're more expensive and they consume more power because they're designed for a much broader set of use cases. So Google has taken the approach of acceleration, which is basically offloading the mathematical computation, and created what is called as a tensor processing unit. So a TPU is a highly customized, purpose-built accelerator. Think of it as an ASIC, an application-specific integrated circuit, which is meant to accelerate TensorFlow operations. You cannot run video rendering on TPU. You cannot do anything other than parallelizing TensorFlow operations. It is tightly coupled with TensorFlow, consumes less power, delivers more performance. And by the way, it's only available in the cloud. You cannot buy a TPU and attach it to one of your machines in the data center. The only way you can consume TPU is by signing up for Google Cloud Platform, launching a Kubernetes cluster or a GCE cluster, and accessing that. So, as I mentioned, TPU is an ASIC exclusively designed for machine learning and AI. And Google has been using it internally to accelerate a lot of operations, including search, translation, photos, and so on. It consumes much less power when compared to traditional GPUs. And as I mentioned earlier, TPUs are available only through GCE and other layers that run on top of GCE like GKE and some of the upcoming technologies like Google Cloud Run. And you cannot run anything other than TensorFlow. And because there is a tight coupling between TensorFlow and TPU, it comes with less overhead, and you don't need additional software libraries or layers like CUDA and cuDNN and drivers to translate your TensorFlow operations to the underlying TPU instructions. So that is the advantage of using TensorFlow with TPU. The most recent version of TPU was launched in 2018, and it is highly optimized for both training and inference. Now it's time for me to differentiate between training and inferencing. So training is basically how you take an existing neural network architecture and apply that to a data set, find features, find patterns. You basically freeze the model when the appropriate set of weights are evolved. So that is basically training, and it uses a technique called backward propagation, where you basically create a complex neural network architecture, and then you use an evaluation data set. So you start with some random set of weights and do a full forward propagation, as in you'll perform all the calculations and you will come out with a prediction at the last layer of the neural network. And then you compare it with the ground truth, which is the original data set. And depending on how far you are from the accuracy, you will go back and course correct the neural network weights. And this process of going back and forth is actually called as machine learning training or deep learning training. And this is highly intensive and requires a massive parallelization, and that's where TPUs come in. So this is training. So once you basically take a neural network architecture, apply a data set, and go back and forth and freeze the weights, that is actually called training. Now, once the weights are frozen, you can take the same model and run it for inferencing. And inferencing is essentially using the model in runtime. So the model is now going to deal with unknown, unseen data, and it applies the frozen weights and parameters, and it only does what is called as a forward propagation, where you don't need to course correct, you don't need to go back and forth. You only take, for example, an image, pass it through the neural network while applying the weights that were already saved and frozen, and then you come out with a prediction. So that is called inferencing. Now, Cloud TPU is essentially meant for training, while Edge TPU is all about inferencing. It is designed to run at the edge. Edge is a computing layer that runs very close to the origin of data. For example, if you have a lot of sensors, if you have a lot of cameras, and these cameras are generating video frames and images at a very fast frames per second, you don't want to take those frames all the way to the cloud and perform inferencing. You want to do it where the camera is. So that layer where we run intelligence and business logic and also a bit of compute storage and network is called the edge computing layer. So because we are running the model there, it makes a lot of sense for us to accelerate the inference, and that is what is called as the AI accelerator. So Edge TPU is Google's AI accelerator that brings the power of TPU to the edge. It has a very tiny footprint. You can actually see in context. It is very, very small. It's almost like a thumbnail. It consumes very less power, something like 2 watts or even lesser, and it is exclusively designed for inference. Of course, it's not completely true. You can do what is called as on-device transfer learning, but 90% of the use cases of Edge TPU are meant for inferencing. It is optimized for TensorFlow Lite. Now, TensorFlow Lite is a framework from Google which is optimized to run TensorFlow models on devices like iOS, excuse me, iPhone, Android, Raspberry Pi, and so on. So Google has extended TF Lite to Edge TPU, and you can pass the model through one more layer of optimization to come out with a very, very small footprint, but very, very accurate when it comes to predictions. It obviously complements Cloud TPU. So Cloud TPU uses it for training, and Edge TPU is meant for inferencing. Now, how do you get started with Edge TPU? I had a full-fledged webinar on this a month ago. You can go to my YouTube channel and take a look at it. But Google Coral is the prototyping platform for Edge TPU. There are 2 devices that come with Google Coral developer kit. One is the dev board that mimics a Raspberry Pi. In fact, its GPIO headers are compatible with Raspberry Pi, and it's a system on chip, which means it's completely an independent device. You power it up, and then it boots into a Debian operating system called Mendel, a Debian flavor. And after that, you can SSH and treat it like a full-blown Linux box. This is one mechanism where you can actually launch your models on an independent standalone device. But if you have an existing edge device that's running a Debian or an Ubuntu operating system, you can also buy what is called as the USB accelerator. Now, this doesn't have the full-blown system. It is just the Edge TPU embedded in a USB form factor, and it comes with a USB-C cable, so you can plug that into a Raspberry Pi or a Raspberry Pi Zero, or pretty much any device that is running Linux. And it basically complements the onboard CPU by accelerating the mathematical computations and inferencing at speed. So coming back to Cloud TPU versus Edge TPU, obviously Edge is meant for inference while Cloud is meant for training. Edge is expected to run only Linux operating system, whereas you can talk to Cloud TPU from a variety of compute services available on GCP. The frameworks that are supported are very limited. TensorFlow Lite and the neural network API, which is a subset of TensorFlow, is available on Edge. Again, you cannot bring non-TensorFlow models like Caffe or PyTorch or MXNet. Obviously, Google is investing in a combination of hardware and software to deliver a unified stack. So it's optimized for TensorFlow. Whereas Cloud TPU, when you're actually running it with Google Cloud, maybe you can use some kind of a translation layer, something like an Onyx, or you can basically go beyond TensorFlow, but it is not meant for that. But using some translators and using some export import tools, you could train with TensorFlow and then export it to scikit-learn or XGBoost or Keras and still take advantage of the underlying TPUs. For example, Keras, even though it's a different framework, the backend is always TensorFlow. So you can technically use Keras, still take advantage of TPU at the backend. So hardware accelerators, cloud TPU, GPU, and CPU, all of them are supported in the cloud. And when it comes to Edge, you can use Edge TPU, GPU, or CPU. Now, Edge TPU is Google's accelerator. NVIDIA has a similar flavor. It's called Jetson. Jetson Nano is the most recent device that comes with a GPU for the Edge. And of course, you can use a variety of CPUs. And by the way, Intel is also one of the players. It has Intel Movidius and Mirai chip and Mustang. It's another accelerator from Intel. You could technically use any of them. But since we are talking about Edge TPU, this is more focused on TensorFlow. So that is a quick walkthrough of what is a GPU, what is a TPU, and the flavors of TPUs. Now, how do you create models and how do you run them at the edge? Well, there are two techniques that Google recommends. One is a no-code approach using the Cloud AutoML Vision platform. And again, I had a session on this last month. If you're not familiar with Cloud AutoML Vision APIs and the platform, watch that video. I basically took a dog breed data set and trained it with 0 lines of code and used it for inferencing. So it's a very powerful AutoML platform where you bring the data set and walk away with a model. And Google has integrated Edge TPU optimization into AutoML Vision, which means when you train a model, you can click a button and basically export that model for Edge TPU and run it on the Edge device for inferencing. So this is one approach. The second approach is basically using transfer learning. It is not meant for beginners. It is not meant for novices. You need to be very, very familiar with the concepts of transfer learning and understand the basics of neural network architecture based on Inception, MobileNet, ResNet, and so on. So basically, you take an existing neural network architecture, you freeze 95% of the layers of the neural network architecture and retrain a couple of layers, and then you get a new model. So that is called transfer learning, and you can use that. So I'm going to show you how to do both of this and then deploy the models for inferencing at the edge. So I don't have a camera. I'm not going to show you what I have here, but just to give you a sense, I have an Intel x86 laptop, and it is attached to a Google USB accelerator. So it is running Ubuntu 18.04, typical Linux box with the USB accelerator plugged into it. So what we'll do is use these two techniques using AutoML and also transfer learning, and then moving those models to my edge device. It's actually not an edge device. It's a very powerful laptop, but we'll treat that like an edge. So let me walk you through the first technique, which is exporting Cloud AutoML Vision model to Edge TPU. So let me walk you through this. So I hope you are still able to see my screen. I have switched to the demo, and I'll walk you through all the steps involved here. So what we're going to do here is to train a new model based on a data set that classifies, that has a lot of flower labels. So basically it's a very very comprehensive data set that comes with about 3,600 images of flowers classified into a variety of types. For example, daisy, roses, sunflowers, dandelion, and so on. And each of these classes have roughly about 600 to 700 images. So what we have done is took a subset of the original flowers data set and first uploaded that to Google Cloud Storage. So here you'll see that I have a cloud storage bucket, and within the cloud storage bucket, I uploaded all the photos of flower. So here you will see a lot of images that are uploaded with some unique identifiers. And then there is also a CSV file which is available here. And this CSV file essentially contains the labels. So it has the path of the original image and with a comma separated delimiter, it also has the label. So we upload the CSV file, and then we also upload all the images into one of these folders. And then we come to AutoML Vision and start the training. So when you actually say new data set, let's say this is MI2 demo, and then you can pass the CSV file path. So here in this bucket, Google Cloud Storage bucket, I have this folder called CSV and all_data.csv. So all I got to do is give the name for the data set and point it to the CSV file, because the CSV file is the laundry list of all the images and the labels. And if you have more than one image in the same image, you can actually click on multi-label classification. This is indirectly talking about single shot detection or single shot multi-box detection. So we don't need to do that because we only have one flower in each image. And then we click on create data set. Now, depending on the size of the data set, it's going to take 15 to 20 minutes. That's the time it took for me to basically create this data set. And then it comes back with this massive data set. And because the CSV file is telling how each of the images are labeled, it automatically classifies them or categorizes them into individual labels. So once the data set is created, next thing is to basically train the model. So you click on train, and then, to save time, I have already gone ahead and finished the training. This took about 2 hours because I used a lot of parameters. And as you see, the precision and recall, they are pretty good, pretty high. And I'm not going to discuss about what is a confusion matrix, what is precision, what is recall. For that, watch my previous video where I covered AutoML. But essentially, when I started training, I chose some options. So let me walk you through it. So when you're using AutoML Vision, you can use cloud hosted model where Google will host the model for inferencing, and you don't need to deal with anything else. It basically throws a REST endpoint, and you can consume that REST endpoint in your app and use it for online inferencing. But if you really want to take it offline, you can choose Edge. And when you choose Edge, you have a lot of options. Low latency, where the accuracy is low, but the turnaround time is pretty quick. So 22 milliseconds. And the size of the model is only 557 KB. It's not even 1 MB. Then if you want highest accuracy, obviously the latency increases. It's about 105 milliseconds. The size is also 5.6 MB. Don't think this is too small. There are some edge devices that cannot even accommodate 1 MB of a model. So 5.6 MB is a lot for an edge device. We are talking about devices that are powered by batteries like CR2302 that typically power your watch. And that device is so constrained for CPU, memory, and storage that 5.6 MB is a stretch. So in those cases, we actually choose the best trade-off, which is somewhere in between highest accuracy and lowest latency. And this gives us the best possible accuracy without increasing the size to 5 or 6 MB. So basically we settle at 3 MB, and 65 millisecond is still quite a bit of latency, but it is okay because we are actually compromising on the size to get better accuracy. And once we choose that, we can target one of the devices. So you see the typical Android and iOS devices. And then there is Edge TPU. So this is the most recent edition. So when you choose Edge TPU, what Google essentially does is it basically trains the model and then finally passes it through another layer which optimizes the model for Edge TPU. And this conversion and compilation deals with what is called as quantization. And again, since most of you are beginners, I'm not going to get into the depth of it, but what happens is the training typically deals with a very precise set of tensors that use floating point 32. So floating point 32 is a pretty large data type. It has multiple decimal multiple numbers after the decimal, and when we train a model with FP32, we get the most accurate, most precise model. But obviously, because FP32 is a large data set, using that at Edge is going to increase the size of the model, and it is quite a bit of heavy lifting for the Edge. So what we need to do is we have to convert the FP32 data type that is used for training to the nearest int8. And int8 is much compact and much smaller data type than FP32. So the conversion that happens from taking a TensorFlow model and targeting TF Lite for Edge TPU essentially deals with converting all the FP32 data types to the nearest int8 with some loss of precision, but maintaining the same level of accuracy. So that process of converting FP32 to int8 without losing the spatial context of the model and the accuracy is called as quantization. So that's what AutoML does when you actually choose Edge TPU. So when you choose this and click on Start Training, the process will kick off, and it will take almost half an hour, 20 to 25 minutes to basically come out with the model. Once the model is done, you can actually click on Evaluate, and you have a confusion matrix, and you have a lot of details about how the model is performing and how it basically evolved through the training process. Then we can move to predict, and here the best thing is you can actually try this with some images. I think I have some images. No, I have it on my other machine, but you can basically upload an image here and test for the accuracy. So let's actually try this. So what we'll do is go to Google and grab a sunflower image, and we will save it locally and test it. So let me grab one of these sunflower images. Yeah, this is good. So okay, this is not too big. So I'm going to open this image and save this as a flower. Okay, and then we will actually try to see the accuracy of this. So now I'm uploading this image, and hopefully the training has been accurate, and there we go, 93% accuracy for this flower being a sunflower. Fantastic. So that's how you can actually test the online prediction. But remember, this is not about running it real time in the cloud, but we want to take the model and move it to the edge. So that's where you can choose the edge model. Now you can actually download the sample camera app that directly uses. Google has done a fantastic job of giving you an Android project and an iOS Xcode project written in Swift or Kotlin, and you can basically prototype an app that actually does the inferencing with the model that's exported here. But our goal is to choose edge device. So we choose edge and then choose one of this. So TF Lite is meant for CPU. So you can actually export this even if you don't use Edge TPU. So TF Lite is pretty good if you are running it on an ARM or x86 CPU. And TensorFlow, if you have, for example, an NVIDIA Jetson Nano or Jetson TX2, and you have a GPU that can understand TensorFlow in its current form, you can choose this. Edge TPU is highly optimized one, and this is what we really want to use. So we choose Edge TPU and click on Export. Now, once you click on Export, what happens is in our cloud storage bucket, we get a new folder. So here you see models, and within that there is Edge, and there is a unique identifier for this model, and the version, which is essentially the date and time, and it gives us the labels file. This dictionary file is nothing but a set of labels that our model was used to train, and then it comes with Edge TPU model.tflight. So this is what is the most interesting aspect, and it is only 873 KB, less than an MB, which is very good. So now what we'll do is download this model, move it over to the Edge. I'm not going to show you the grunt work of SCP and all of that. So I have already gone ahead and saved this model to my Edge device. So all I can show you, okay, looks like, okay, my machine, I think, went into sleep. These are the challenges of doing a live demo. The host is down. Give me a second while I wake up my machine and come back. All right. So this is an indication that I'm actually doing a live demo and not faking. So you get to see what I'm doing here. All right. So now I logged on to my AI test bed, and this AI test bed is actually not an Edge. It is a very powerful x86 machine with an NVIDIA GPU thrown into it. It's a custom built gear, but I'm treating it like my Edge for now. So what we'll do is to basically test the model. So in the directory called demo, I have another directory called AutoML, and what you notice here is the same TF-Lite file that I have downloaded from this Google Cloud Storage bucket and renamed it to avoid confusion. It's called AutoML Edge TPU TF-Lite, and I renamed dig.txt to labels.txt, and all it has is the index and the actual class. So straightforward. Now what we'll do is I have already installed the Edge TPU SDK. So I'm moving into one of the directories installed when you launch the Google Corel Edge installer. So here there are a bunch of Python files, and one of the Python file that we're going to use is classify image. So what we'll do now is to basically take this sample script that shipped with the SDK called classify image.py and pass the model that AutoML has generated, the TF-Lite model, optimize it for Edge TPU. And we'll also pass the labels, because this is what is going to tell the classifier on what label to look up. And then we have a random flower by name flower2.jpg, and we pass that as the input image. So let's go ahead and run this. So I'm going to grab this and run the classifier. So this is pretty fast, 92% accuracy, and it is actually showing a sunflower. Exactly, the flower image that I passed is definitely a sunflower. I'm using that consistently for all the demos, but to deliberately avoid any kind of bias, I didn't name it as sunflower. It's some random flower2.jpg, but the model was intelligent enough to figure that it's a sunflower, and we got a pretty decent score. And this is straight from Cloud AutoML Vision API. Fantastic. So again, as you have seen, this is a no code approach. I have not done anything except creating a data set and then click on a couple of buttons and just wait for half an hour, and then I got the model fully generated. So this is one preferred way of of generating a TensorFlow model, highly optimized for Edge TPU. But AutoML is like a wizard, and not every use case, not every data science project, not every deep learning project can fit into the AutoML flow and the framework. A lot of times you need to do hyperparameter tuning. A lot of times you need to take control of the neural network architecture, and you need to have more transparency in the way the model is built. And who knows, you might actually want to build something from the scratch. or leverage an existing neural network architecture like MobileNet or Inception or ResNet or LXNet or one of those. So that is the next thing that I want to talk to you about. So the hard way of converting TensorFlow models for Edge TPU is to go through a very systematic process. So here we train a 32-bit floating point, which is FP32 TensorFlow model, and then we turn that into an 8-bit fixed number. This is the quantization I was talking about. And then you export the checkpoint into a frozen graph, which is a Protobuf. It's a PB file, a language and platform agnostic format to make TensorFlow files more portable. And once that is generated, we basically convert that into a TensorFlow Lite file. And till now, we are not even aware of Edge TPU. Now, this step that you are seeing here is basically the precursor to Edge TPU. So the output of this step, when we generate a .tf Lite, essentially the model is ready to run inside a mobile device, like a Samsung Galaxy or a Google Pixel or any Android or iOS phone. That model, that format cannot be directly executed on Edge TPU. You need to take it through one more level where we actually convert the TensorFlow Lite to an Edge TPU TensorFlow Lite. So there is a subtle difference between the TF Lite generated for mobile devices versus the TF Lite generated for Edge TPU. So we need to go through that. So this is quite a bit of process, and it is complex, but a lot of data scientists and a lot of enterprises and industrial customers are actually going to prefer this because it puts them in a lot of control. And you can do everything on-prem. The reason why customers would choose this versus AutoML is in cloud. For example, you want to take very sensitive patient data and you want to perform inferencing at the edge. And obviously your local policies and sovereignty and governance policies prevent you from uploading sensitive patient data to the cloud, and you want to run it locally. So since there is no AutoML in your data center, obviously it's a secret sauce of Google, you need to create your own model, your own architecture, and that's where this comes in. So now let me actually walk you through this. I spent 2 days learning this and trying to come out with the entire process. It is still very raw. There are some rough edges, but remember, both Corel Dev Kit is not in production. It is still in preview. So the TF Lite SDK, Edge TPU SDK, all of that, they're just getting aligned. Right now, there are some issues, there are some rough edges that we need to go through, but eventually this will become much smoother. So let me set the context. So the first one was a wizard style. 3 clicks, boom, we have a model that we could deploy to Edge TPU. But this is very complex. So what I've done is, by the way, my AI test bed, which I have been proudly claiming as a very powerful environment, has actually crashed when I ran this image classification training. So then I had to launch a GCE instance with 16 cores, I think 16 cores and 60 GB memory, and actually ran the training on the cloud, and then installed the Edge TPU SDK and converted the model. So let me actually play a video, because if I do this as a live demo, it would take 6 to 8 hours. So I'm going to walk you through this and pause at appropriate steps and tell you what's being done. So right. So I hope you are still able to follow. So obviously what you're seeing here is I'm launching a GCE instance. So this GCE instance, let me pause here. So it is basically running launch this all over again. Okay. And it's running Ubuntu 18.04. Okay, I'm not sure how the experience is, but this was the best possible effort to bring this demo. So now I've also opened port 6006 to basically expose the tensor board, because I'm going to show you the training process in tensor board. So once the instance was launched, I SSH'd into it. So here you will see that I'm getting into the VM. Right after that, we install Docker, and I build a Docker image that has a TensorFlow runtime. And then I basically clone the TensorFlow models. So here, okay, let me let me show you what I have here. Oh, this is frustrating. I can't go back. Okay, so so let me pause here, while I'm able to pause. So I created a Docker image that contains the TensorFlow framework, and then I also git clone the research branch of the TensorFlow GitHub repo. And within that, there is a script that basically gets us the data set and prepares it. So this data set is the flowers data set that we have used earlier with cloud.ml, but here I'm actually grabbing that, all the images in JPEG, and then turning them into the TensorFlow native format called. It downloaded the zip file, the tar file of the flowers, and then it's going to base. Okay, GoToWebinar is muting me. I don't know why. So now we converted the images from standard JPEG to TF record, and then we are kicking off the training process. So here you'll actually see a lot of parameters that are being passed, and this is a standard transfer learning based on MobileNet, and this is going to bring up the tensor board, where we can actually visualize the training process. Again, nothing special so far. It is just the way we train any other TensorFlow model. And if you're not able to follow this, this video will be up on YouTube. I've also documented this as a tutorial at the new stack. That should be up very soon. So now the training process is happening, and this is transfer learning. The number of steps I have chosen is 300. So what we are doing here is taking the flowers data set, taking MobileNet SSD v1, and retraining that model, freezing certain layers of the neural network, and only keeping certain retrainable. So now at some point here, if you carefully observe, this is going to finish and save the model to the disk. There we go. So now it has finished the training and it saved the model to the disk. So at this point, what we got is a typical TensorFlow checkpoint. We can verify that by getting into the CKPT directory. And we'll notice that there are a bunch of checkpoint files based on MobileNet. Now, the first step here is to convert the checkpoint into a protobuf. So that's what is being done here. So we are now taking the checkpoint. All right. So by end of this process, we will get a new directory called models. And within that, we will actually notice that there is a frozen graph file. And of course, we also created the TF Lite, which is now ready to be run inside a mobile device. But that's not all. We need to now turn this into an Edge TPU compatible model. So I'm installing the Edge TPU SDK and the CLI. So now we get a tool, excuse me, we get a tool called Edge TPU. So now we will take that CLI, the tool called Edge TPU convert, Edge TPU compiler, and generate the final Edge TPU TF Lite. So this is the file that we're going to use in our live environment. All right, so that was a quick walkthrough. Again, not sure how much of that could be followed, but I can actually run the last part of the conversion for your understanding. So now what we can actually do is, these are the steps involved in installing the Edge TPU CLI. So basically Google gives us a repository where we can install the Edge TPU SDK and the CLI tool from a simple apt-get install. So once we have the TF Lite model, we can run the Edge TPU compiler to turn that into the Edge TPU optimized TF Lite model. So let me show you that. So inside the demo directory, I have models, and within the model, I have a directory called Edge. And currently this has this has multiple files. So let me get rid of them. No, this is empty. So what we'll actually do is to move the TF Lite file that that was generated from transfer learning. So we'll actually copy the original TF Lite into this directory. Okay. Right. So now this is the TF Lite that TensorFlow would typically generate. Now our goal is to take that and optimize it for Edge TPU. So what we'll do now is take that TF Lite file and run it through Edge TPU compiler, and this will now give us a new file called edgetpu.tflite, and this is what we are interested in. We'll also copy the labels.txt into this directory. So now we have everything that we need: the Edge TPU optimized TF Lite file and the labels.txt. So with that in place, we can go back and run the inference all over again. So let me switch to the directory where we have the classify SDK, the Edge TPU SDK with the classifier, and we will run the new TF Lite that we just generated inside this Edge directory. So everything remains the same, just that we are pointing this to a different model and a different image. So even this is a sunflower image, and the score is, again, it is confused between sunflower and dandelion. It is saying 60% probability that the flower is a sunflower, which is actually fine. With some more training and some more hyperparameter tuning, I can get this to a better accuracy. So this is the handcrafted, completely custom built Edge TPU TF Lite model based on transfer learning. Now, the other way of doing it is, don't use transfer learning, create your own convolutional neural network, but that is going to be extremely complex, not meant for faint-hearted. You need a proper CNN specialist and someone who understands how convolution works, and then build the entire neural network architecture. So that's the other way. So that basically brings us to the end of the second demo. To summarize what we have done, basically we have taken existing TensorFlow models, either trained in the cloud through AutoML or using transfer learning, and ran it through an optimization process, which is nothing but a compilation and quantization, and ultimately run it at the edge. So some of the interesting data points: TPUs deliver end-to-end AI infrastructure, training in the cloud, inferencing at the edge. Edge TPUs are extremely small, consume less power, optimize it for inference, and they can only run TensorFlow Lite. That too, optimize it for Edge TPU. You cannot bring a generic TF Lite supposed to run inside an Android to the Edge TPU. Cloud AutoML models can be exported with a few clicks. We have seen that. And Edge TPU compiler can be used to convert TF Lite models generated via transfer learning or any other mechanism. So that brings us to the end of this session. Now, I want to thank our sponsors. Newstack, our media partner. By tomorrow evening this time, you'll actually have a tutorial and an article up and running where I talk about this whole background, and that is like a transcription of my session. So you can keep an eye on the Newstack to get that article. Foghorn, a Bay Area based multi-cloud edge intelligence company. Portworx, a container native storage company, again based in Las Altas, Bay Area. I want to thank our sponsors. Though the logo is missing, Google is one of our premium sponsors. They came on board recently. I want to thank Google for supporting me with all the background, context, and validation of these demos and all of that, and also supporting me with credits and the infrastructure for all these demos. I'm very excited to announce the next session on September 26th, and we are shifting gears to the infrastructure track. And I'm going to talk to you about how to apply zero trust security for GKE, Google Kubernetes Engine. So we'll talk about configuring networking policies. How do we secure communication between pod to pod, pod to service to service, ingress, egress, everything that you need to know about networking policies that can be applied to GKE clusters running in production. So this is on September 26th, same time, and I'm looking forward to having you. Go ahead and register at mi2.live. If you're watching this on YouTube, in the description, I'm going to add the links to the slide deck, to the tutorial, and if there are any scripts that I'm going to upload to GitHub or as a gist, I'm going to include them as well. So that's it. That brings us to the end of this session, and I want to bring up a quick poll before you leave GoToWebinar. So let me bring up this poll. How relevant was the webinar content? Did it match your expectations? All right. Most of you tell me that it is very relevant. I appreciate that. Thank you for your honest feedback. There are some people who think it is somewhat relevant. And I know I had to balance between explaining what the TPU is and what TensorFlow is before we could jump into this. And I have one final poll. So how do you rate the overall quality? This includes my delivery, the quality of demos, the audio visual experience, and the 1 hour that you have spent with me. Thank you. Everyone felt it is good. Most of you actually felt it is very good, and some of you felt it is excellent. That's very encouraging. I'm committed to bring you high quality content on modern infrastructure and machine intelligence. Thanks again. And subscribe to my YouTube channel. Go to YouTube and search for Janakiram MSV, and you will hit my channel, subscribe. And I'm going to upload these videos very often. And keep an eye on mi2.live. Do sign up for my upcoming webinars. I will see you in the next session. Thank you, and have a great rest of the week.